The universal set is a set that contains every element under consideration. Like the name implies, it is universal. That means all possible elements that is being considered in the set is the universal set. When we consider the set of students in a class, every member of the class, both the male and the female students, are part of the universal set. Now, every other set being considered are subsets of the universal set. Like in the case of a classroom, you may have the set of boys, a set of girls, a set of students above the age of 15, a set of students above the age of 18. Those are subsets, but the universal set comprises every element being considered. Now, the universal set is denoted with this symbol mu. It can also be denoted with this symbol sigma, and like we said, every other set is a subset of it, so it is like the mother of all of them. The universal set gives birth to every other set being considered. Next is the empty set. The empty set is a set that contains no element. That means when you check the set, it does not have any element. An example is set of female presidents of the United States of America is an empty set. The empty set is denoted by this symbol phi, and it can also be called the null set, which you can represent as a set without any element. So this is a representation of the empty set. If you look at the content is what? Empty. So it is called a null set. Next is the singleton set. It's like the name implies, single. That means it has only one element. So when you check the contents of the set or the family, you see that it will just have one member. It is like, some people call it a lonely set, but in this case we call it a singleton set or a unit set because it contains one element. So if we can have set A that has one element 3. This is an example of a singleton set. We can have set B that has one element 0. This is an example of singleton set. We can have this that have an element phi. This is also a singleton set, although some people confuse this as an empty set, but no, this is not an empty set. This is a set that contains one element phi. So don't confuse it with an empty set. When this phi is standing alone, like here, this is an empty set. You can say set A is an empty set, but in this case set C contains, because this is an alphabet, so it is not an empty set, rather it is a singleton set. Now we select our universal set be a set of single digit numbers ranging from 0 to 9, and we have our set A as this, which is clearly the set of odd numbers, and set B the set of even numbers, set C and set D. Now I want to look into some terminologies in set, and first we look at the cardinality of sets. Cardinality of a set is the number of elements contained in a set and is denoted by the letter n. So from this given here, we say that the cardinality of set A, that is this way, is what? The number of elements 1, 2, 3, 4, 5. So the cardinality of set A is 5. The cardinality of set B is 4, because it has 4 elements. So that's the definition of cardinality. Whenever you see cardinality, it talks of the number of elements in a set. The cardinality of set C is 1. So set C is a singleton set from our definition. Next we look into complements of a set. Also that given a set B, which is a subset of the universal set, that the members of the universal set which are not in set B constitute the complement of B. Now from this our case, we know that this is our set B. Then the complements of set B are those sets that are in the universal set which are not in B, and is denoted by B prime or B complement. So for this case now, we have that B complement is equal to the set 0, 1, 3, 5, 7 and 9, because from the definition you see that these members of the universal set are not in B, so they constitute the complement of B. So when you look now for this our set C complement, you can say that C complement or C prime is equal to set D, because when you look at set D, every element in the universal set that are not in this set C are in D. So C complement is D, while D complement is C. So if you have that C complement equal to D, that means D complement is equal to C. Now this is a quick exercise. We say if mu is the universal set, then the complement of the universal set is what? Put your answer in the comment below. Let's see. Next is the intersection of sets. The intersection of two sets A and D is a set which consists of elements that are both in A and D. In this case, we say that A is denoted A intersection D. It comprises of sets that are in A and also in D. That means if this set, if an element is in A but is not in D, it is not part of the intersection. And if an element is in D but is not in A, it's not part of the intersection. So from this our case, we see that A intersection D is equal to what? 1, 3, 5, 7, 9, which is the same thing as what we have in A. You see that these elements are both in A and D. 2, for example, 2 is in D but it's not in A. It's not part of the intersection. Now when we look at the intersection of A and B, we see that there is no element that is in A but and in B. That means the intersection is either we say it's empty this way, or we say is an empty set. So this is how we deal with intersection of sets. Moving further, we look into the union of sets. The union of sets A and B is the set which consists of elements that are either in A or in B or in both A and B. So we see that from the definition, union is more free, because if a set is here or is here or is in both of them, it forms the union. So it is denoted A union B equals the set such that X is an element of A, or X is an element of B, or X is an element of A and B. That is A intersection B. So you see that intersection is contained inside the union for this set. So for this our case, we see that A union B is 1, 2, 3, 4, 5, 6, 7, 8, 9. So which is obviously set D. So this is the union of A and B. You see that this one is not here but is in the union from the definition. Moving further, we look at the disjoint sets. We see that two sets A and B are disjoint if they do not have any common elements. That means there are no elements that can be found in A and also found in B. This implies that A intersection B is equal to the empty set. In this case, we see that the two sets are disjoint. If you observe this our set up here, you see that there is no element that is common between A and B. So A intersection B is empty. That means set A and set B are disjoint. But set A and set B are not disjoint. Set A and set B are disjoint because this element is not here. They don't have anything in common. So they are disjoint. So that's the definition. So we say that A intersection C equals the empty set. This is a disjoint set. A and C are disjoint. So next we look at the power set. So that the power set of a set V is the set of all subsets of V, and the power set of V is denoted by, this is called the power set of V. Now if we have set V as, this is our set V now, then the power set of V is the set of all the possible subsets that can be formed from V. In this case, they are sets. These are the power sets. They are subsets. The set of subsets, that is what the power set implies. A, B, and the empty set, sorry. 1, 2, 3, 4, 5, 6, 7, 8. So this is the power set of V. That's if this is our set V. That's from the definition of power set. From the power set of V we just showed, we saw that our set V has 3 elements, and the power set of V comprises of what? 8 elements. That is 8 subsets formed the power set of V. So we observe that in general, if the cardinality of V is M, which in the previous case is 3, then the cardinality of the power set, that is the total number of elements that will be in the power set, is 2 raised to power M. From our example, we saw that V, cardinality of V is 3. Then the cardinality of the power set of V, which we saw that is 8. Cardinality of the power set of V is equal to 2 raised to power 3, which is 8. So this is how to know the number of elements of a power set, even without writing out the set. You just use this general formula. 2 raised to power the cardinality of the set, so it gives you the number of elements in the power set. So in this video here, we solve problems that regard the Venn diagram. So thank you very much. Subscribe.